Okay, so why don't we start up again with the next section? So we're looking at 10.2, and we're going to be talking about vectors. And you might have seen vectors before in another class, or maybe you learned it on your own. The concept is not too crazy, but first let's start with a definition. So a vector which we'll kind of denote with a arrow on top of the symbol. In this case, this is the vector v. In Rn, meaning that we're in the reals with a dimensionality of n. This is a quantity that has both a magnitude and a direction. Okay, so a vector might look just something like an arrow, right? Where it has a initial point and a terminal point. So this is, maybe we call this A, and this is our initial point. And this might be the point B, and this is our terminal point. So a vector just simply has a magnitude, basically being the length of the vector, and it points somewhere. So let's talk about how these things start to interact with one another. So if I have the two vectors, we'll call U and V, and if they have the same magnitude, and the same direction. Then we have that we'll call U and V equal. Makes sense, right? They denote the same information. They have the same magnitude, they have the same direction. So these vectors are equivalent, and we'll say that this means that they are equal. So now by introducing this concept, we actually have to talk about the zero vector. The zero vector which we'll denote with just a zero with the vector symbol on top, has no length and thus no direction. Okay, so now that we've got kind of vectors down, we've introduced this concept of a vector that has no length, doesn't point anywhere, the zero vector. Let's talk about addition. Sorry that my handwriting on this tablet is not as good as I would like to. Hopefully we'll improve as we go on here. Okay, so now we have to talk about the act of summing vectors together. So what does it mean to add two vectors? Well, if I have a vector like this, well, let's do it like this. And I have another vector that's like this. And we'll call this one over here, this is our u. And this one over here, this is our v vector. Then the idea of the addition between u and v is that what I'll do is, let's write it down here, u plus v will look like if I had taken this vector here, let's copy and paste it. Ooh, that's nice. Can't do this on a blackboard. And then we'll copy and paste this guy here. And I'll connect the initial point to the terminal point of the other one. And now, if I connect the beginning to the end of the second one, I've created the vector u plus v. So this down here was our u vector, and that right here was our v vector. And it's cool because it doesn't matter which way I did this, right? Because that's actually how addition should work, right? The order should stay the same. So let's kind of tuck this in a little bit closer here. Now, if I did v first, looks like this is gonna overlap. It's fine. And then I did this guy here, voila. I have the same resulting vector, the hypotenuse that I create from each triangle, right? And this stays the same. So it doesn't matter if you do the first one or the second one first, or u or v first, it still makes the resulting vector here, this hypotenuse, the addition of the two. That's one nice feature about this remote learning. Okay. So another name for this property, let's scroll down a little bit more. This is also known as the triangle law. And notice that what we just talked about the order of addition not mattering, this is called the parallelogram law. Because it makes a parallelogram. Okay. So now that we've kind of discussed addition, let's talk about scalar multiplication. Okay, so we have to throw in the scalar out in front because we'll learn about what happens when we multiply, and that's like air quotes, vectors together. That won't be until a little bit later. So if we have some constant scalar value, we'll call it C, and it exists in the reals. If you haven't seen this like epsilon, it just means that it exists in the set that's to the right of it. So you have some constant value in the reals. So it's just a real value. And it's multiplying onto some vector v. So we have C times this vector, what we'll call v. What happens in this scalar multiplication? Well, C simply scales the magnitude of v. So C scales the vector. More specifically, let's say the vector's magnitude by the value of C. Okay, so let's look at an example. If I had a new vector, let's call it v, and I wanted to know what 2v looks like, we'll notice that we can kind of use addition laws to help us out with that. 2v is the same as saying v plus v. Okay. Well, now let's go ahead and take our vector v and let's make two of them and use our addition laws to help us out. So we stack them together like that. And now we've created some vector that's still in the same direction as v was, but now it is twice as long. So where we had v and v here, this is 2v. Okay, so now you might be asking yourself, that's fine for like a positive value of c, but what happens if I have a negative value here? And then if I have a negative value, I can also talk about what it means to do kind of subtraction. So a negative scalar switches the direction to the opposite of the original vector. So now let's imagine that I wanted to look at a negative v, right? Well, negative v, I'll try my best to kind of draw this. I don't know if I can flip it, is the same magnitude of v, but pointed in the opposite direction. So let's kind of move that over here. Right? So it basically swaps the terminal and initial point, right? But more like that it kind of passes through the initial point here. So if you think about it as, let's do a copy and paste again. So if this was v, they both still have the same initial point, but their terminal points are now exact opposite, mirrored of one another. So let's say this is v, and this is our negative v. Okay, so by this, we can actually talk about subtraction. So subtracting vectors can kind of be seen as adding the negative. So if I have a u and I subtract a v, we can write this as u plus the negative of v, right? So now let me draw some more vectors here. Let's do a u, and let's do a vertical one for v for kind of simplicity here. So if this is our u and this is our v, we're also going to need a negative v like that. Okay. So here is our u vector. Here is our v vector. And the first thing we need is this negative v. And now we're adding u to this negative v. So let's do another copy and paste here. We've got our u. We've got our negative v. And the resulting vector is this guy there. So this was our u. This was our negative v. And this is our u minus v. So subtraction is just a special case of this scalar multiplication and our addition, right? So all we did if we do subtraction is we think about what happens when we do the negative of the vector and then do our simple addition rules. Okay. So let's continue. Let's go to a new page. Now let's talk about components. So sometimes it's convenient to write vectors not as this like graphical representation, but to write them possibly as descriptive as possible, meaning we're going to talk about how much it goes in the x direction, how much it goes in the y direction, and so on. So let's first look at a vector in R2. And, oh, maybe I should have just drawn arrows for those as well. But I have some vector here, v. Well, I can write this, if this ends at the point v1, v2, so now this is a point, but the vector can be written, and now notice that these are sharp, not like parentheses, these are sharp brackets, that this is v1, v2, and then I end them. So this vector v points to the point v1, v2, but it is written as this sharp bracket v1, v2. And this was in R2. So now let's do R3. So for z, we have our y, and we have our x. Ooh, let's make it a little bit. Yeah, there we go. Okay, so now I have some vector. We'll call this one u. And u goes to the point here. I'll call this u1, u2, and u3. And you can imagine that we can still write this very similar. It is the vector u1, u2, and u3. So think about it like this. This one had a v1 x length. It had a v2 y length. And that's what we gave this description here. It goes a distance of v1 in the x direction and a distance of v2 in the y direction. Whereas in R3, let's also write that, R3, that we're going u1 in the x direction, u2 in the y direction, and u3 in the z direction. So there's a difference between writing it as a point and as a vector. So now let's talk about how addition, subtraction, scalar multiplication works when we're displaying it in this format, right? Can we kind of quantify how that behaves? Yeah, of course we can. So if I have a u vector in this case, and we'll kind of write it similar to above, so u1, u2, and u3. And we also now have a vector v that is v1, v2, and v3. Okay, so there's a few things we can read right off the bat. These vectors are in R3 because they have 3 components, right? They're in 3-dimensional space. Great. So now let's look at how these interact. So if I have, let's scroll up a little bit. If I have that u and I add a v to it, I can write this as u1, u2, and u3 added to v1, v2, and v3. Or what I can do is do this component-wise, where I can have that u1 added to v1, u2 is added to v2, and u3 is added to v3. And that's my new vector, right? Because if I changed by x in this one, and then I added a vector that changed by x by v1, then the resulting change in x is definitely going to be u1 plus v1. And same thing with the y component and the z component of our vectors. So now if I have a scalar multiplication of these vectors, so we have our constant c again, and I multiply it by my vector v. We can write this as c times the vector v1, v2, and v3. Or another way of writing this is that c gets multiplied to every single component. Like so. And this scales the vector by a length of c. So most of this class, we're going to be talking about vectors not as graphically, but more in this kind of notation. Okay. So another characteristic that we need to be able to kind of calculate and keep track of is magnitude. Because I've said that vectors have direction and magnitude. Well, how do we calculate this magnitude? So the magnitude of the vector v written as it looks like double absolute values on v. Sometimes you might see this with 1 bar instead of 2 bars. I think it's common to kind of simplify this in physics or maybe chemistry, that you kind of reduce this notation to 1 bar. I'm fine because you guys are engineers if you want to write this with 1 bar rather than 2 bars. But know that this is kind of the notation for the magnitude of a vector. And it makes sense, right? This same notation is the magnitude for a scalar value, meaning what's the magnitude of -5, right? It's 5, right? And in the same kind of context, what does that magnitude mean? is the distance between the initial and terminal point. Right, and that makes sense. When you're talking about just scalar values, saying like, what is the magnitude of -5? It is the distance from the origin that -5 has. It's 5 units away, right? This is very similar, right? What is the distance between the initial point and the terminal point? So in R2, let's use the single one this time. So yeah, at least use both. This will be the square root of the change in x squared plus the change in y squared. So it should look pretty, pretty similar, right? And if we had the components of v1 and v2, and our vector was centered at the origin, this is v1 squared plus v2 squared. In R3, let's use the other one. So we have double. This is the square root of the change in x squared plus the change in y squared plus the change in z squared. Right? And if our vector v has the components v1, v2, v3, then of course we can write this as v1 squared plus v2 squared plus v3 squared. So basically it's just the distance formula with the change in x and y and z all being the components of our vector. Okay. So let's do another example. Let's find the magnitude of 2u minus 4v when u is equal to 3, -1, 5, and v is equal to 0, -3, 2. Okay. So before we kind of dive in here, let's talk about what we might need to calculate, right? Well, we're going to have to calculate the magnitude of the vector that's inside here, this 2u minus 4v. But to do that, I need the vector that's 2u, and I also need the vector -4v, right? So why don't we go ahead and calculate those first off? So we have 2u. And now, because we're doing a scalar multiplication, remember it's multiplying each component. So we have 2 times 3, 2 times -1, and 2 times 5. This gives us the vector 6, -2, and positive 10. Now we have negative for v. Same thing, we're going to multiply by -4 on all of these components. So we have -4 times 0. We have -4 times -3. And we have -4 times 2. So then we have 0, 12, and -8. So those are 2 vectors. And now we need to find what 2u minus 4v is equal to? Well, this is our 2u, wrote that small, 2u plus our negative 4v. And we can write that as 6, negative 2, and 10 plus our vector 0, 12, and negative 8. Or 6 plus 0, negative 2 plus 12, and 10 minus 8. Where the vector is 6, 10, and 2. Okay, so we're not quite done yet. We have the vector that's inside this magnitude, and we still need to calculate the magnitude. So let's continue. So the magnitude of 2u minus 4v is the square root of 6 squared plus 10 squared plus 2 squared, all in a square root. So we get the square root of 140, or another way of writing that is 2 times the square root of 35. So that's kind of the procedure for doing an example like this, right? I first had to find the vector that's inside this magnitude, and to do so, I first found 2u, and then I found negative 4v. I did the addition of our vectors there, and then I finally found the magnitude. Maybe that was a little bit drawn out, but it was our first time kind of interacting with this, so now we've seen it. Okay, another thing that's going to pop up in this course a lot is unit vectors. So let's kind of define them here. A unit vector is a vector with unit length, or magnitude of 1. So unit vectors are really nice to kind of detail direction because they only have a magnitude of 1. So we're going to use them for describing the x, y, z directions by kind of saying like an x hat, or later we'll call it I hat, and so on. So we'll have like an I hat or an X hat, a Y hat, and a Z hat. And then we'll also kind of talk about decomposing these vectors in terms of unit vectors. We're also going to use them later on to kind of dictate where things are going and where they're accelerating and stuff like that. But for now, unit vector. They have a length of 1. Okay, so we have about 15 more minutes. Why don't we talk about some properties of vectors? All right, so there's a few of these. First one, and we've seen this one already, but let's jot it down in our list, is if I have a vector u and v and I add them together, it does not matter which order I add them in. If I have v and I add to it the 0 vector, I don't change my vector v at all. If I have a scalar multiplied by the addition of u plus v, I can write this as c times u plus c times v. So the scalar can distribute, which is a nice property. If I have two constants, c times d, and they're multiplied on a vector v, I can write this as c times d times v. Right, so it doesn't matter in which order you multiply these scalars and the single vector. Okay, another property is if I have maybe the addition of 3 vectors. So I have u plus the sum of v plus w. I can write this as u plus v plus w. Again, it doesn't matter which I do first out of the additions for vectors. Okay. If I have v and I add to it this negative v, this is how I produce the 0 vector. If I have a scalar sum, so a constant c plus d, and it is now multiplied on a vector v, I can write this as cv plus dv. And finally, if I have the scalar 1 and I multiply it by my vector, I just get my vector back. Now, these might seem pretty simple, and they probably feel pretty intuitive with the algebra that you're used to. That's because the space that vectors live in is really nice. If you ever go on to take analysis, you'll kind of understand why. But vectors being based in the space of Rn, meaning the collection of the reals in an arbitrary dimension n, is a really, really nice set. Otherwise, some of these properties might not be true. So we're lucky that we live in this kind of world. Okay, so we have about 10 minutes left, and we actually concluded section 10.2, and I think that's what we were going to start up tomorrow. So we're a little bit ahead. So why don't we stop there for today, unless you guys have any questions or you just want to stick around for another 10 minutes. I'll stay on if you have any questions, you know, of today's material or just the course in general. Other than that, I will see you all tomorrow. Stay safe, and I'll see you then.
Thank you.